I plan to, as technology doesn't fail me, I will record these classes and put them up on the Canvas page and also on my YouTube channel. Please don't consider that a substitute for coming to class. I promise you, your life will be much easier if you just come to class. The recordings are kind of for backup, come down with, Ebola or something and have to miss a couple of days, then the recordings are there. And also, I hope that this frees you up to just listen to class, so you don't feel like you have to take notes. The notes that I will follow are notes that are actually posted. They're posted on my webpage. They're on Canvas. It's just notes. There will be typos in there, but hopefully you can just add to those a little bit as you go along. So I like to free you up to participate in class as much as possible. So I will come in, I will record the class. There is a Zoom option up there in case for whatever reason you can't make a class one day, but please try to be here. It covers a multitude of sins, believe me. So there are the homework in this class is worth 50%, and I'll talk more about the homework later. We'll have 2 exams. One of them September 26th, the other one November 7th. It'll be worth 15% apiece, and then the final exam will be worth 20%. So I've got a 90, 80, 70 scale. That is a worst case scenario. So if you get a 90, so you all have 3190, right?
Yeah.
If you get a 90, you get an A. I did not say if and only if. So see if you can figure that one out. Canvas will generate numbers because anyway, don't trust anything that I haven't put in, right? I will give you a daily briefing on what your grade is, if that's what you want to know, and I will do an official update after every exam. Office hours, I've got a lot of them, take advantage of that. Need help. There is no attendance policy in the sense that I'm not going to take attendance, you don't have to be here, but I recommend that you do this. If you've gotten behind or if you have to miss the class, make sure that you're caught up on things. Yes, just make an AI policy, which is a great idea. AI is out there, we all know it. If you use it at all, just be careful.
Yeah, at this point it's useless math now because it requires a lot of proof and probably get to
Well, it does get better as things go along, but it will. The problem is it acts like it knows what it's doing, and oftentimes it doesn't. So you gotta get real useless with it. Homework is the biggest piece of your grade. It's half your grade. And I will try to be very punctual about getting your homework back to you. I don't have any grading support this semester, but I think I can be mostly a good boy. So you will get problems on the homework that are out of 3 points, some out of 5 points maybe. There also might be some G problems on there if they're graduate students in the class. The graduate students that have to do this class. Undergraduates do not have to do, but if you do them, I will record them for extra credit. And the G problems, the graduate problems, if they're on there's not any on the first one, will be worth 5 points. I am going to be suits hard on when it comes to grading your homework, right? I'm going to nitpick you. I'm going to, my whole thing's being equal. It's going to be important for you to do it right. It's going to be important for clarity. And I'm going to pick on you because I want you to have feedback. I don't want you to give you 3 out of 3 or 5 out of 5 when there's little things there that need to be improved, because I want you to get feedback on this. Now, take heart, little soldiers, because of this, I will curve the average homework around about an 80, right? At least an 80. So again, that curve goes on as the course goes on. So I can tell you, it's like, oh my gosh, I've got a 40 average on this. Just come ask me and I'll tell you where you really are. Okay. So if you're in the middle of the class, as far as your homework average, but you're getting back on the homeworks, and I'm going to be hard on everybody, then that's going to put you at about 80 anyway. So anyway, I don't want you to get intimidated or anything. So nobody should make any serious decisions about, oh my gosh, I should drop this class. Don't ever do that without talking to me or your other instructors, for that matter, probably. Okay, any questions on that? Alrighty, so let me set that up here on board. And, this first. There we go. Okay, so I have already put your first homework, which will be due not this Friday, next, and I traditionally have to say. So this doesn't look like abstract algebra yet. In fact, I think a lot of you probably saw some of this stuff at least.
No.
3190.
Yeah, it's also something 4190, which took over the summer.
This is, these are properties of the integers. And so why do we do this? Mostly properties of the integers instead, because this is a fundamental part of abstract algebra, right? We're talking about mathematical structures and things that are much more general. Is that, is that, so these are some basic properties, the integers, and some stuff about sets that I want you to go over. Hopefully you've seen some before, but you know, ironically, I think some of these problems are a little bit subtle, but they're important because the properties of the integers have to come up with structural groups and rings. Okay, so the first problem is, suppose the km and n are just integers. Are y'all familiar with the symbol?
Yeah, I know. I'm pretty familiar with that.
And I want them to be non-zero. Show that the greatest common divisor of m and n is a linear combination of m and n. So in other words, if I had two numbers like 7 and well, that's actually 14 and 105, say, the greatest common divisor of that turns out to be 7. And you can also write the greatest common divisor as a linear combination. So 7 is 14 times some integer plus 105 times something else, which is not readily true. I would sort of start with this, right? So my hint on this problem is find the smallest linear combination of m and n and show us the greatest common divisor. These are some other important properties. Show if the greatest common divisor of m and n is 1. So that is, they have no non-trivial factor in common, and the greatest common divisor of k and n is 1, and the greatest common divisor of k and mn is 1. Show if the greatest common divisor of k and m is 1, and k divides mn, then k divides n. By the way, I am going to review today what the greatest common divisor is, but is everybody familiar with this?
That's not the greatest common divisor.
So let m and n be positive integers. Let D be the greatest common divisor of m and n, and L the least common multiple of m and n. Show that when you multiply the greatest common divisor and the least common multiple, you get the product of m and n. Number 3, let S be a non-equal set. Show that if tilde is an equivalence relation on S, then the set of equivalence classes under tilde forms a partition of the set S, so it breaks it up into.
You can also 4190 as well.
Right. And I'll review what these words mean. Show that if PI is a partition of S, then there's an equivalence relation such that the sets PI are precisely the distinct equivalence classes of S are under that equivalence relation. Okay. And finally, number 4, the Chinese remainder theorem. This is kind of an interesting one, and it has many, many applications actually. Show that if n1, n2 up to nk is a collection of pairwise relatively prime positive integers, and n is the product of all these. Show that the system of congruence is x is equivalent to a1 mod n1, x is equivalent to a2 mod n2, all the way up to x is equivalent to ak mod n. Has a unique solution z between 0 and n minus 1, where n is this big animal here. So that's hopefully that's some things that you've seen at least in some context before, but you know, that'll be due next Friday, and if you have any problems, just give me a call. Okay, any questions before we get back to it? So okay. What's up?
Just the 3D film.
Oh, yeah. Somebody worked hard on that. Okay, so I'm going to start this off with what I call kind of warm up. I'm gonna hit some things in broad strokes what, we probably need for this.
I also have filled in them for linear analysis.
Oh, gee. Y'all seen these symbols?
Yeah, I
before?
have.
This is the natural numbers, and in my class, the natural numbers start at 1. If I want the natural numbers to include 0, I'll use that notation. The integers, which is now throw in the negatives, right? The real numbers, this reminds me of calculus, right? The complex numbers, right? All A plus BI, where A and B are real numbers, and the rational numbers. Can somebody describe what it means for a number to be rational?
Basically, there exists, I can represent them by the division of two integers. Or
Okay, right, it's a fraction. A over B, where A and B are integers and B is not 0. So, another important concept is the one of functions. Let A, B, C, D be non-empty sets. I don't want to fool around with silliness here. And I'm drawing the empty sets. Let F, let B, D from B to C state. Now, if you might recall from 3190, the functions are defined as in terms of something called relations here. But I'm going to start with functions right now and talk a little bit about relations later. It's a generalization of functions. But remember, what does a function mean? It means that it's sort of a little machine you might think about that it takes A to B, input A, output B. Everything in A can be plugged in. And what makes it a function?
Also, basically, that for any result in A has only one definite result in B.
Right. So any given output has only one output.
It's well defined.
That is correct. So if I have, this was pictorially. So F is a function that takes A. B is G is a function that takes B to C. The image of F, and sometimes this is written F in capital A. Well, this is just all the stuff that's sort of hit by the function. That is. This is all images. And it is a subset of B. Anybody remember this one? Suppose D is a subset of B. Right. This is sometimes called preimage. Anybody remember what this is?
So it's basically all the elements in like A that basically when you plug a function there, it's also an element in D.
Okay, so let me I think what you said is correct. This is all the stuff in A, such that F of A lands. So this is A, this is B, and this bit is D. In this case, what's F inverse D? It's the empty set, right? There's nothing here that lands in that.
Yeah.
Okay, good. And like I said, this set is called pre-image. Um, uh, if set D is just a single point, then F inverse B set of A in A such that F of A is B. And this is sometimes called the fiber of that.
We be using like that D is an E notation for more or.
No, this is just kind of, I don't think I'm gonna excessively use that. I mean, actually, and if you're trying to criticize me, which is always kind of a good idea, it might be more clear for me to do that. Right, I think of it as a set, right? Because the way I had it written before, it sort of gives the illusion that F inverse is a function, it doesn't. Right? And given this setup here, the composite function. If you look at the composition of G and F, from A to C, this is called composite. G composed with F, and it is fine. Just kind of ride the train. F takes A to this guy that lives in B, and I'm not done with my train ride yet. And G takes it on to C. Right? A goes to F, and B goes on to.
What's the between F and B?
It's a circle, but sometimes people.
Oh, okay.
Yeah, it's
Yeah,
just a composition thing. And usually I'll suppress that unless I feel it needs to be emphasized.
I was on a second.
Oh, I'm sorry.
Oh, okay.
That was supposed to be an and.
Okay.
Okay. Here's a couple of important definitions. Again, using my notation that F goes from A to B and G goes from B to C. F is 1-to-1 or injective. Anybody remember how we find this?
It's basically that one injective is like every element in B like that is basically the image of F will basically have like only one result in A. Corresponding to this.
Let me make that a little more precise.
So if A1 will equal F of A2, if and only if A1 equals A2. I think that's the answer to that one, you know. At least also if and only if, you know.
F of A1 is so in other words, if the images are the same, if A1 and A2 go to the same place, then they had to be equal in the first group. Two, F is onto. And if I want to. So fancy, I might say subjective. If. Yes.
Is it A1 equals A2 implies the pre-image of A1 is the pre-image of A2 of A2?
What it means to be onto is everything in B has to be met, right? It has to be the image.
Yeah.
If for all B and B. There exists A through such that F of A. So nobody in B is wrong with that. Okay. Three, yeah. F is 1 to 1 and onto. We say. F is. Both working.
Bijective.
And number 4. F has a left. Respectively. Right. Inverse. If there exists H, B to A, such that, that works. Uh, you see it's got a left inverse. There's some function that comes back from B such that when you do F, then you do H, you get, this is the identity function on A. So when I say that 1A, that is the function from A to A that takes everything to itself. This is the right inverse, right? Do H and then F, and you get the identity. Okay. And of course, if you have a function that is, well, what can you say about a bijective function?
It's left and right.
That's right. It has both a left and right inverse, and and it's the same. That's exactly right.
Can you explain like why it's called the left and the right inverse? I just like how can you tell which one's left, right?
Well, let me give you an example.
Okay.
An example. So suppose that F, let's say that F is this. See, and in fact, we'll sort of go along with this little theorem here on the way. Okay, so if you look at this function here, I'm going to draw a function that's 1 to 1. Would everybody agree that all of this is what I call A and this is what I call?
I wouldn't say that's one because it doesn't cover every element in B.
Don't have to.
Oh, it has a subset. That's fun.
So would everybody agree that this is 1 to 1?
Yeah.
But it's not onto, right? Okay, so can anybody think of what a left inverse would be? Oh, let me do the easy part. Where does this one go? It's an adult. Let it go wherever it wants. Doesn't matter. I'm going to call this function right here H. F is, I should have put F in white or something. No. Now let's see what happens. Now, according to this, what happens when I do, well, I know what should happen. This, if I've done this example right, it should be the identity of A. Let's see what happens here. When I do, well, what happens when I start here and I do F to it and then H? When I start here, I get back here. When I start here, I get back here. When I start here, I get back here. Everybody agree? So when I do F then H, everybody agree I get the identity on that? Doesn't work the other way though, does it, right? Because what happens when I do? If I start here and then go back, I haven't changed anything. If I start here and go back, I haven't changed anything. If I start here and go back, I haven't changed anything. Almost there, right? What happens if I start here and go back? Well, because this function wasn't on to, there's no way I'm getting back here. It's not happening. So when I go here and then back, I get something different. Right? So this is a good example of a function that has a left inverse, but it doesn't have the inverse that you're used to from the old days, right? And by the way, how many left inverses does this have? Well, for the picture I've drawn, it's got
Can we have like each of them, like?
because it only depends on the choice of where this road goes, right?
It'll be
And the road
three.
could have gone here, here, here.
Three left inverses because of the three different permutations we said, say.
So is that clear?
Yeah, what about respective right? Or you, RASP right, what is that?
That means that left, if you replace the word left by right, then replace this by this.
Okay,
So that's, yeah, thank you for bringing that up. So sometimes theorems are written like this for definition. This means replace left by right, means replace what's in parentheses, this with what's in parentheses.
oh.
Okay, other questions? All right. Proposition 1. So here's kind of a fun thing. We'll do a little bit of this, maybe. Proposition 1. Let's suppose that f from A to B is a function. I will implicitly assume sets are not empty. So this function's empty. 1. F is 1-to-1 if and only if f has a left inverse. F is onto. Anybody want to guess this one?
We're gonna have those inverse.
Good question. Number 3. F is bijected. If and only if F has a two-sided inverse. That is, the left inverse and the right inverse coincide. If both of them to the right coincide. Right. Let me clear here. There exists G B to A. Right, such that we have G, it's the identity on B. We do G F, yeah. And finally, I like this one. Yeah. Suppose that A and B are they're sets. Suppose they have same size for the first statement, and the size is fine. That's actually very important. Then F is injected if and only if F is certain. If and only if F is finite. So if you have a finite set, well, if A and B are finite sets the same size and there's a one-to-one map from A to B, it has to be onto it. Right, and if it's onto it, it has to be one-to-one. This is wildly not for infinite sets. Yes,
So the line, that's cardinality.
yes, that's correct. That's correct.
Well, I know you should probably, like, shouldn't you use a left null instead of infinity, because there's kind of two kinds of infinities when you deal with infinite sets.
There's actually infinitely many kinds of so. But right now, all we need is any infinite set, so.
Let's put a left null here.
So. Let me sketch. Because I think it might be a good warm-up exercise for you all to work through some of these. Suppose. Yeah. 1, 1. Actually, no, let's actually do it the other way. Part, because this is the hard direction. We'll do it this way. Suppose F has a left and we want to show that F is 1, 1, correct? So any ideas on how we might go about that?
Probably we have like for every single thing in F A, like in A, you probably do F of A, then use the left inverse to bring it back there to prove that projection that needs to produce a 1-to-1 set.
So this is what it means for F to have a left inverse. Here I'm going to call it G. So when I do F of G, I get the identity on that, right? So that's one little tool here that I'm going to do this. Now suppose F of A1, yeah, so A1 and A2. To show it's 1-to-1, what conclusion do I need to come to? I need to somehow dig out of this that A1 and A2 are the same thing, right? That's what it means to be 1-to-1, right? Well, I've already got this. So why don't I just get a shovel and dump that into G? Let me show you how to do that. I took these two things because they're the same thing and I plugged them into the function G. Right? Now, what happens when you do F and G? You get the identity on A. That's because G is left inverse of that, right? And what happens? The identity of A on A1 just leaves it as A1. And this is A2. So I've come to the conclusion. Okay, I'm not going to finish this completely, but I'll show you what the answer is the other direction. And we sort of did this problem over here. Now, suppose F in AB is 1-to-1. We've got to build, right? We've got to go crazy like Noah and build the inverse, well, left inverse, right? Think about what we did here, right? Remember the original thing, F was the white arrows that went over here. What did I first do with the orange arrows? How did I decide where this goes? I sent it by. This is what I'm gonna do. I'm gonna define. Hey, look. And there's gonna be a couple steps to it. Of course. Size two doesn't make that. How am I gonna do this? I'm gonna look at my B over here. And what's the first thing I should probably do? That is right. I'll look at my B and I say, hey, Mr. B, do you come from something over an A? Is there an arrow pointing to it? Right? And so I will let this be A if F of A is B. Everybody okay with that?
That's all you figure it out.
Now, there's something that concerns me now. There's something that maybe should bother you. Set off a little alarm. What's that? What might you worry about here? Right. Well,
Coloring value.
there isn't one. And she's absolutely right. There isn't one, and I'm going to get to that problem later. But let's just suppose, for the sake of giggles, that there is one. There's still a problem that I might have to worry about. What's that? Right. What if there's a whole bunch of different things? What if my choice of A is not unique? Maybe there's 1,000 A's that go to B. Maybe there's infinitely many A's that go to B.
That's picking on it.
But it's 1-to-1. This is where we use the 1-to-1. So this choice is unique. If B is F, because F is 1. There can't be two different A's to go to that same B. So I've totally conquered that problem. But Cassie, we gotta get back to your problem. The other problem is, what if there ain't none?
Just figure in a value in A.
Okay. Yeah, right. Here. X is. L. And that's essentially what we did here. We had a road here that didn't have a white arrow going to it. I just sent it back somewhere and it doesn't matter. It still worked to be a left inverse, right? That last statement does use that first assumption. Like, what did I assume that the sets are not empty? I'm in trouble here if A is the empty set, right? Yes, sir.
Can you like state what the problem was with that first part? I didn't really understand what the problem was that made you use the one to one. The first line. Said the
Well,
problem-
so what I do is I say, okay, my input is B, and I look at B and I say, hey, I'm just gonna send you back to the A you came from. What if it came from many A's?
Okay, but it
Right.
didn't.
But I don't have to worry about that. There's no choice to make.
Yeah.
Because facts.
Yeah.
Okay, other questions? Okay, I encourage you to try to finish up some of the other proofs to kind of warm you up. To all this. Let me get
So
through.
all of those propositions are correct.
Yes, yes, this is a.
It's in target now.
Well, I mean, he's right, because technically a proposition is a statement that is either true or false. When I write the word proposition up here in this class, I will be, that it's, unless I get some words wrong, it's supposed to be right. Okay, definition. Put A, B, A9. A relation, in relation on A. In 3190, you probably did something more general, relations from A to B. I'm not gonna worry about this so much here. Is a subset of A cross W. Because in algebra, we're gonna need like relations on a particular subplot. Or so it's a way to relate things. We say that the ordered pair A1, A2, we say A1 is related to A2 if that ordered pair appears in that relation. A1 related to A2, if A1, A2, that ordered pair is in R. Now, this is a rather abstract way to think about it, and we'll get to something more practical when we actually start using this. Two. The relationship tilde or the relation tilde reflects it if A is related to itself. So the ordered pair AA is always in there. B, symmetric. If A is related to B, implies B is related to A. So if A is related to B, then it has to be true. The reverse is true. That B is related to A. And transitive. If A is related for all. A is related to B, and B related to C, implies A is related to C. Transitive relations are very important. Of course, not all relations are transitive, right? I mean, I like to use, we've got football season coming up, so I always like to use that example. Football is not transitive, nobody would watch it. Team A beats Team B, Team B beats Team C. That does not mean that Team A beats Team C. Otherwise, it's kind of not as exciting. C. If tilde is reflexive, symmetric, and transitive, it is called an equivalence. If we have an equivalence relation, so building up again, if tilde is an equivalence relation on A, then, well, let's see, and A is in A, so A is some element thing. Then the equivalence class of A So, give an equivalence relation on set and pick some element out of it. In the equivalence class today, anybody remember what this is? Right. It's everything in X, or it's every X in A, such that X is latent, whatever this is. And finally, did I? I sure did. Now, it's gonna look like I'm having a stroke here, because you're gonna think that that's totally gone off the rails, right? But I'm gonna tell you what a partition is. If A is not an empty set, a partition of A is a collection of non-empty subsets of A. We'll say I is an index set. And this partition has the following properties. What does it mean here? So it's just a collection of, yeah, it's a non-empty subsets such that A is equal to the union of all of these. And two, AI intersect AJ is empty. If I is not empty. Here I is ever indices, set I. So what it means to be a partition is it's like a jigsaw puzzle, right? These are the pieces of the jigsaw puzzle. When you put all the pieces together, what do you get? You get the whole big picture. And jigsaw puzzles would suck if this weren't true. There, oh my God, two of these jigsaw pieces are stuck together, bad, right? So partition, there's no overlap in the whole thing. So what's the point of all this? Well, it turns out that equivalence relations form a partition, or a set of equivalence classes form a partition, and every partition is a collection of equivalence classes. You're going to prove that at home. Okay, any questions? Yes.
There are reasons you say collections, such.
Other questions? Yes,
You have the, what is I there, that
I is an index set, right? So it might be the natural numbers, it might be a finite set, there might be only 6 sets, for example. Others.
Okay.
All right, y'all have a good one. We will see you. Actually, you will see my substitute on Friday. I've got to be out of town, so it will be office hour Friday, but I will be back and things will be on the rails on Monday.
I'm excited to see Finland.
Good.
But I-
Monday then.
You see the great distribution.